You have seen how to program a node that publishes and subscribes to topics using the Python programming language. This time, let's see how we can do the same thing with C++. ROS2 Foxy targets C++14, so we can write modern C++ with ROS, whether it's functional or object-oriented programming. From the previous lesson, we already know the objective of the code. On your terminal, go to the workspace you created earlier in the course and source the workspace. Go to the source folder of the package you created in the previous lesson and use the touch command to create a C++ executable. Let's call it avoidwall.cpp. Go back to the workspace and open VS Code or any convenient text editor from there. Our ROS code depends on some header files, which we will include before writing the main body of the code. The first is a C++ header, while the others are ROS headers. The second header is a ROS client library for C++, and the last two is for the message interface needed to move and turn the turtle. We'll come back to the placeholders and chronoliterals later. Usually, the best type of code structure you want to use for ROS2 is object-oriented programming. We start by creating a class avoidWall, which inherits the properties of the ROS C++ client library node. It means our avoidWall class can access members of the ROS C++ node class. Then we define how members of the avoidWall class can be accessed. The public specifier can be accessed by all parts of the program, while anything in the private specifier is only accessible to member functions of the avoidWall class, not the code used in the class. Let's declare some private variables. We'll declare a speed publisher variable. The data type a publisher variable uses follows the syntax. First is RCL-CPP, which stands for the ROS client library for C++, and then the scope operator publisher. So RCL-CPP publisher, followed by the type of the message or the message type used by the publisher, an optional shared pointer, and the name of the variable. The subscriber variable follows a similar syntax. Then we create a variable that handles the rate at which the speed of the turtle will be published. This is called timer. Create a speed variable of geometry trees type and two float variables that stores the pose of the turtle in X and Y direction. Let's create a callback function that gets the pose of the turtle and stores it in pose X and pose Y. We'll call this callback function pose_callback that takes a constant parameter called turtlePose, which is of type turtleSimPose as seen on the header library or when we introspect via the terminal. Use the arrow operator to access the variable in X in the turtlePose and store the value in poseX. Repeat the step for pose_Y. We'll create another function that will make the turtle go forward and turn based on the information we get from the pose. Use the dot operator to access the linear speed of the turtle in the X direction and initialize it to 2.0 meters per second. This means the turtle will always move forward 2 meters per second. The turtle simulator environment is about 11 by 11 unit, and we want the turtle to turn when it approaches the extreme of the shape or the extreme of the wall. We'll define a limit of 1 and 10. So let's set the condition for the robot to turn. If the pose in X direction is less than or equal to 1 or greater than or equal to 10, or pose in Y direction is less than or equal to 1 or greater than or equal to 10, then we want the angular speed of the robot about the Z-axis to be set to the value of pi or 180 degrees. If that condition is false, the angular speed should be set to 0. So basically, we're saying that when the turtle is close to the wall, the turtle should turn. When the turtle is not close to the wall, it should keep moving forward. Let's publish the speed to effect the changes in value. If you don't publish the speed to velocity command, the turtle will not move. Let's go back to the public specifier to create and initialize a publisher, subscriber, and timer. Without that, our publisher and subscriber will not know what topic to publish or subscribe to. Create a constructor from the class avoidWall and pass the node name avoidWall as a parameter. We already declared a speed publisher variable as speed underscore pub underscore. To initialize it by creating the publisher, we follow this syntax. Type this, which is a keyword referring to the node, which is an entry point to creating subscribers and publishers. Use the arrow operator to access the create publisher. Pass in the message type of the topic name you want to publish to, and the quality of service, which is 10. Quality of service, QoS, as we said earlier, is a policy that helps in handling communication between nodes and how traffic is prioritized. According to ROS, the default QoS settings for publishers and subscriptions is 10. Create a subscription the same way publisher was created with a little difference. After the QoS, bind the callback with the aid of a placeholder, which is _1. And that's where the placeholder we created before the class comes in. Similar structure for the timer underscore. The 10 millisecond is an STD chronoliteral in C++, which means we will trigger the speed timer callback every 10 milliseconds. We've written it up substance. Our code is yet to run without the main function. Init initializes the node while spin processes information in the class until shutdown is called by a process like Ctrl+C on your keyboard. We're done with the code. Let's set up the compilation instruction for the code to run. Open the CMake file under your package. Add the ROS client library package dependency with the geometry message and TurtleSim dependencies. Create a C++ executable. After the keyword add executable, type the executable name and the executable file showing its directory. Link your project dependencies to the executable you just created. The last thing is to install the executables. Save your file and open the package.xml. This is where we define what our package depends on. Our package depends on RCL-CPP, the ROS client library for C++, geometry messages, and TurtleSim. Save your file, build your package again from the workspace directory, and source your workspace overlay. Now you can run the node to see how great your code is. Beautiful, the turtle moves forward and subscribes to the post topic every time. When the post value shows the turtle is close to the wall, it publishes an angular speed that makes it turn as it keeps moving forward. There are few improvements that can be made on this code as we discussed before. For instance, you'll observe the turtle only turns to the left, even when turning right seems appropriate.